Okay, so hopefully you got some sort of notebook out by now that we're going to write some things down. Okay, so today the plan is to talk about equilibrium. So if you're at home and you want to do this activity, I just put them through the ringer, and they had to do a really hard activity where they explored equilibrium. So you probably find something online, but theirs was extremely challenging. So probably glad you weren't here. So anyways, but that activity right there was supposed to express the challenge of chemical equilibrium. Okay. In normal reactions, or in all the reactions that we talked about so far, they're one-sided. You have starting substances and then they go through to produce reactants, right? Well, starting today, and I'm going to go ahead and switch this over to the screen so we can look at the notes. Today, we're going to start talking about reactions that are reversible. Okay, reversible reactions. And this is many reactions in science are considered to be in chemical equilibrium. Or in other words, you start with some starting substances, you start with some reactants, then they react, they produce products, but then when you have too many products, they start to break back down and go back to what they came from. And you have this constant equilibrium. In your body, you have reactions that are always at equilibrium. Your body produces, or your body has a substance called hemoglobin, which will help transport oxygen. It carries oxygen through your blood. It deposits them at cells. When you have too much CO2 in your cells and in your blood, it will transport CO2 back out. You have this constant coming and going of oxygen and CO2, and that's an equilibrium reaction. Okay? So what is chemical equilibrium? Do you know how many paper? Yeah. Well, if you have a notebook or any paper at all, like I think you should probably write it down, or you can type it in your Chromebook. Yeah, probably a good idea. Chemical equilibrium, it's the state of a reaction. The state of a reaction where there's no net charge or change. So net change. When there's no net change of reactants and products during the forward and the reverse reactions. The state of a reaction when there's no net change of reactants and products during the forward and reverse reactions. Much like what we were doing today with the beakers and the pipettes and trying to get your liquid over into the other person's beaker, it's extremely challenging to try to keep that going at a consistent rate, right? And some of you felt like maybe you got behind and that's how you got your butt whooped, all right? And some of us just have no hand strength. That's my problem, yeah. Clearly, that was the case. Not because Niyush is better, it's just because I'm old, okay? So whenever you have this constant coming and going of products and reactants, when they start going at a balance, when you have consistent amounts coming and going, that's called equilibrium. Most systems want to be at equilibrium, okay? They want to keep a state of equilibrium, all right? So if you think about traffic in a big city, you don't have to write this down. This is just an example of traffic in a big city. When the amount of cars going into the city is the same as the amount of cars going out, there's no net change of car population, okay? If we were able this morning to have exactly the same amount of liquid going up into our pipette, and both of the people were able to do that, sucking the same amount of liquid coming up and putting it in the other person's without losing anything on the counter or without squirting somebody else in the eye, you would have no net change. You would have a system at equilibrium. But the way that it was in some of our beakers this morning, we had maybe more of a forward reaction, whoever would want to be the forward reaction, and maybe less of the reverse reaction, which is why some of you ended up with some of your beakers had like 60 milliliters of fluid and the other person might have, 20 or whatever it was. Okay. All right. A really good example, one of the most famous examples of a system at equilibrium is called the Haber-Bosch process or the Haber process. You guys learn about this in Germany? Because he's famous. So. But Fritz Haber is the guy who came up with the Haber-Bosch process. There was a guy that came along like 20 years later. So Fritz Haber came up with this process to make ammonia. And about 20 years later, in the 1930s, there was another guy by the name of Bosch, and he came and perfected the process. So, okay, but the Haber process is the process of making ammonia. Okay, so it's the process to create ammonia. All right. The process to create ammonia. It was actually discovered just before World War I. Right? Yeah. World War I was known as the Chemical War. So you had lots of scientists all across the world trying to find out ways to build better chemical weaponry. So you have all these brilliant scientists working on this for their country. And he actually discovered this process to mass produce ammonia, NH3. Yikes. Terrible idea.
Well, that's what they did.
Well, and you heard like in the 60s, like there were lots of housewives that were dying because they were mixing bleach and ammonia. So they had to start putting like warnings out there for all of the women who were trying to make that ultra good cleaner with ammonia and bleach. They were killing themselves trying to clean their toilet. They were passing out and dying. Yeah. So, well, and what we're going to learn about this week. So tomorrow, your Win Wednesday assignment, you're going to do a little bit of research with Fritz Haber. He was a very interesting individual. One of his most famous quotes was, during peacetime, a scientist belongs to the world, but during wartime, he belongs to his country. Okay, and we're going to look at that over the next couple of days. And I want you, as you do your research assignment tomorrow, we're going to talk about some questions that I want you to ask yourself and think about when your country is at war, how do you decide for yourself what is ethical and what is good for the country? Okay, what is good for your country and what is good for the world? Because science and ethics go hand in hand, just like science and math go hand in hand a lot. Okay, so we're going to take a look at this. Why would ammonia production be such a big deal back in the early 1900s? What's ammonia used for? Do you know? Refrigeration, yes. What else? And think farming.
Oh, it's fertilizer.
Fertilizers, yes. So this mass production of ammonia using chemical equilibrium, knowledge about equilibrium, it would mass produce ammonia so that way they could mass produce fertilizers. Basically, this was one of the most world-changing events in the 20th century because the population of the world was exploding and people were starving everywhere. With the production of ammonia to mass produce fertilizers, they were able to produce enough food to feed, millions and millions of people. Without the mass production of ammonia, like scientists and social scientists, people who study like populations and stuff, said that probably half of the world's population would have starved to death with the amount of people that were still coming in. And we just didn't have enough food to feed them. But with the mass production of ammonia, we were able to feed all these people. You're able to produce crops.
these following students: Valerie Moreau, Sarah Goldberg, Ethan Strecker, Terrence York.
Okay. This principle helped Fritz Haber create the Haber process. And I'm going to totally butcher this. Have you had French, Vito? Good. Okay, so you won't know if I screw this up. Have any of you had French? Okay, all right. I'm going to go with Le Chatelier. Because I think, like, most people from Arkansas would be like, Le Chatelier. I don't think that's right, though. It's Le Chatelier, maybe. Anyways, we're going with that. It's horrible, like, when I have, like, kids come over from, you guys, I don't know, y'all were freshmen back then, but do you remember Giacomo Tuccio? And love Giacomo. And, oh, shoot. Hope he didn't ever watch this video. What was the other one's name? Felix. There was Felix, but no, there was one more. Oleksiy Korotik from Ukraine. Anyways, those guys had French, or at least one of them had, I think. Anyways, and every time I would say this, he would giggle. He'd be like, "You're saying it wrong." And I was like, "Shut up." Anyways, this is Le Chatelier's principle. Okay. What? See, I was so close. Le Chatelier. Wait, do it again, one more time.
Oh, I just.
Oh, dang it. Sorry.
No, it's gone.
Oh,
Le Chatelier.
Le Chatelier. Oh, so there is a little bit of an in there. Okay. That person's probably from Arkansas on there. Le Chatelier. All right. Anyways, this guy came up with this principle. This Frenchman came up with this principle a few years before, about the same time that Fritz Haber was working on this process. Well, this principle basically says, if a change is applied to a system at equilibrium, if a change is applied to a system at equilibrium, the system will shift. The system will shift in the direction to reduce that change. If a change is applied to a system at equilibrium, the system will shift in the direction to reduce that change. Okay, so think of it like this. If you had a teeter-totter, you guys know what I'm talking about, like a seesaw? Okay. If you had a teeter-totter or a seesaw out on the playground, and you had two kids of approximately equal size and mass, they would have a great time going up and down, okay? If you add another kid onto one end, that throws the system out of equilibrium or out of balance. So how do you fix the system of the teeter-totter? Yeah, put another kid on the other side of approximately the same mass, or make that other kid get off, right? You do something that's going to reduce the change in the system. Today, whenever you guys were trying to get all of your water into the other person's beaker, okay, if there was a change in the system, so for instance, if you end up with a hand cramp right in the middle and you can't do anything about it, is there going to be a change or a shift in equilibrium? Yes. One of the beakers is going to end up with more fluid in it because there was a change in the system. According to Le Chatelier's principle, then, the system would try to correct itself to reduce that change, which means that probably whoever was pumping like crazy into the other beaker would slow down and back off until the system could go back to equilibrium, until you could have equal amounts in both beakers. Le Chatelier's principle says the system is always going to try to shift in a direction to eliminate the change. They want to stay in balance. The system wants to be at balance in nature. So according to this principle, the system will do whatever it takes to keep it at equilibrium. Okay, so the ways that it can do this then, changes that could be applied to a system, which is going to cause a shift, are changes in concentration, pressure, or temperature. If you have changes in concentration, pressure, or temperature. Okay, so if the system that you're looking at gets changed in its concentration, its pressure, or its temperature, the system is going to try to shift in a direction to reduce the change. It's going to try to shift to make it go back into balance. All right, so let's play a little game called Predict It. All right, you don't have to write this down necessarily. I do want you to look at these and try to come up with in your mind what direction they would shift, okay? So here we go. All right. Right here, you have carbon dioxide, hydrogen gas, and it produces water vapor and carbon monoxide. This is the system that we're looking at, okay? If you add a drying agent that absorbs water, so in this little reaction, we're going to add a drying agent that's going to suck out water and water vapor. You need to think about what's going to happen to the system and how would the system shift in order to correct itself, okay? So first of all, if you're adding a drying agent to absorb water, where do you see the water in the equation? Right here, okay? It's on the product side, right? So if you're taking water out of the product side, the system wants to have water as a product. So the system is going to need to make more water, right? So is it going to shift to make more products or less products? Would it shift to the right to make more, or would it shift back to the left to make less water? What do you think? It should shift to the right to make more. The system, if water is going to get taken out on the product side, the system should shift right in order to make more. Does that make sense? Okay, take a look. All right, you have salt, solid salt. You're mixing it with some sulfuric acid right here. It creates an aqueous solution, or sorry, a solid solution, looks like I ate you, of sodium sulfate and then hydrogen chloride gas, a toxic gas, okay? If this reaction is carried out in an open container, how is the system going to shift in order to keep equilibrium, to keep balance, okay? Now let's think about this. You have a solid and a liquid that's mixing together to create a solid and a gas, and it's being done in an open container. It's going to shift to the right. Why do you think so?
Because the gas is
Yeah. If the gas is in an open container, it's going to leave the container, right? It's going to leave the system. You want to keep equilibrium. You want to make sure that you have hydrogen chloride gas there the whole time. So you either need to close the container or just keep having the products react. You're going to continue to have it shift to the right. You're going to go in the forward direction, okay? Put this one, okay? Take a look at that. You have solid silver chloride, AgCl, and when it breaks down in solution, like if you put it in water, it produces silver ions and chloride ions, okay? So you put silver chloride in water, it breaks apart into little ions and they float around. If you add some aqueous sodium chloride, so you're going to add some salt, which is going to break apart into water, and it's added to the solution. So now you have sodium ions and chloride ions floating around aqueous. How is the system going to shift? To the left? What do you guys think? Shifts left. But why? And Peyton can't say it.
Because, you have it into it's like what was reacting.
You would have, when you take that NaCl and it breaks apart, you end up with more chloride ions floating around on this side. There's too many. Like the teeter-totter is unbalanced. You've got too many, so it's going to shift back to the left to get rid of some of those floating chloride ions. Okay? So when that goes into the water, you've got too many on this side. It's going to shift back to the left to reduce some of that. Okay. Last one. Or did I do one more? I can't remember. Okay. N2 plus 3H2 yields 2 NH3. So this is, this can be the Haber process, because this is the process to produce ammonia. Okay, if you add a catalyst to speed up the reaction, right? That's what we did yesterday, by the way. We added a catalyst, that potassium iodide, those 10 drops that we added, that was the catalyst that sped up the reaction, okay? So what do you think? Shift right, shift left, or no change? Right? Okay, this one's weird.
Or no change.
No change. Yeah. This one, because of the fact, guys, a catalyst, when you put it in a chemical reaction, a catalyst doesn't have anything to do with the chemicals that are there. All it does is speed up a reaction. That's all it's there for, is to change the rate. But it doesn't have any effect on reactants or products. Okay? All right. Here's the last thing you've got to do for today. All right? These questions here, I would like you to go ahead and write them down or type them in your Google Docs. These are the things that you're going to have to research tomorrow on Wednesday. You need to come in prepared to discuss them on Thursday. Okay? So if you'll write these questions down for Fritz Haber. I'm going to put that back up there here in just a second. I'm going to go ahead and turn this off, though.